Welcome. So today we're going to do something pretty bold. We're going to try and build the rulebook for reality itself. We're diving straight into the core logic of quantum theory. Those strange, beautiful, and honestly kind of weird rules that govern absolutely everything at the tiniest scales. So let's just kick things off with a huge question. See, to understand the universe down at the level of atoms and particles, the old rules of physics, the ones that work so well for, planets and baseballs, they just completely fall apart. We need a totally new rulebook, and you're about to see it is a profoundly weird one. Okay, here's our game plan. First, we're going to see why we need a whole new language just to talk about this stuff. Then, we'll learn its basic grammar, things called questions and states. After that, we'll find the engine that makes it all run, which is all about probability. We'll explore its bizarre relationship with time, and finally, we'll meet the master tool that can predict what happens in every particle collision in the universe. Let's do it. All right, let's get into it. The first thing we have to do is kind of rewire our brains a little bit. The quantum world just doesn't operate on the same logic we're used to in our everyday lives. It's a whole different ballgame. This right here, this is the single biggest leap you have to make. At its very heart, quantum theory is all about probabilities. So you have to forget about asking, hey, where is that electron, and expecting a straight answer. The only valid question is more like, okay, if I look for it, what are the chances I'll find the electron right here? It's a universe built on odds, not certainties. So how do you even begin to build a theory out of something as fuzzy as probability? Well, you start with two fundamental building blocks, something called questions and something called states. Okay, so this is postulate 1, rule number 1 of the game. It says that every single simple yes or no question you can possibly ask, like, is this particle spinning up, gets its own mathematical tool. It's called a projection operator. You can think of it like a special filter designed for just that one question. The operator, this P, is the question, just translated into the language of math. And that's really the genius of this whole framework. We're not just asking things in English anymore. We're actually encoding the act of asking a question into the math itself. That symbol, P, literally represents the question we want to ask. So, if P is our question, what exactly are we asking it about? Well, that's where the state comes in. And postulate 2 gives the state its own mathematical identity too. But here's the really crucial, mind-bending part. The state isn't the particle itself. The source defines it as the body of information available about the system. It's not the thing. It's a mathematical summary of everything we know about the thing. So now we've got our two key players on the field. We've got P, which is the math for our question, and we've got rho, which is the math for all the information we have about the system. We have the question and we have the subject of our question. Okay, so we have our question, P, and we have our state, rho. Great, so what? How do we actually get an answer? Well, this brings us to the real engine room of the entire theory. Postulate 3 is the magic key that unlocks everything. It tells us that the probability of getting a yes to our question is found by combining the question operator, P, with the state operator, rho, in a very specific mathematical way. This is it. This is how quantum mechanics actually makes predictions. And there it is, the recipe itself. Now, don't worry about the symbols. That's not the important part for us. The point is this. This is the engine. You feed it the question, P, and you feed it the state, rho, and it spits out a number. And that number is the exact probability of getting a yes answer. This simple-looking formula is the source of every single prediction quantum mechanics has ever made. It's incredible. Fantastic. So we can now get a probabilistic snapshot of a system at one specific moment. But, things in the universe tend to move. They don't stand still. So how do we get from one moment to the next? How does the whole system evolve through time? And that brings us to postulate 5. This introduces the master controller of time in the quantum world, an operator called the Hamiltonian, or H. Just think of the Hamiltonian as the system's own internal rulebook for how to change, and it's all based on its total energy. The Hamiltonian then creates another operator, U, which acts like the hand that literally turns the clock, pushing the system's state forward from one moment to the next. And this equation you see here? That's basically the gear mechanism for that master clock. It shows exactly how the Hamiltonian H depicts how things change. This is the mathematical heartbeat of the quantum universe. Okay, now this is where things get really, really fascinating.
So the theory gives us this mechanism for how time works, but it also says there isn't just one way to look at it. There are actually different but equally correct points of view.
You got to check this out. On the left, you have the Schrödinger picture. In this view, the state of the particle, that body of information we talked about, is what evolves and changes through time. But the questions you can ask about it, those are fixed. Then, on the right, you have the Heisenberg picture. Here, it's the total opposite. The state is completely frozen in time, but the questions themselves are what change and evolve. So, does the information change, or do the questions change? The amazing answer is yes, both perspectives give you the exact same correct answers at the end of the day. And it doesn't even stop there. As the source material points out, for even more complicated setups, there's a third, kind of hybrid view called the Dirac picture. And in this one, both the states and the questions are allowed to change over time. It all just comes down to picking whichever perspective is easiest for the problem you're trying to solve. So now we have all the pieces. We've got states, questions, probabilities, and time evolution. Let's put it all to work on a real-world problem. What actually happens when two particles smash into each other? For that, we need one final incredibly powerful tool. So here's the crucial point. Imagine two particles flying towards each other from opposite ends of the universe. They interact, they do their thing, and then they fly away. How on earth do you connect the before picture to the after picture? We need one last piece of machinery to do that. And that tool is called the S operator, or the S matrix. It is the ultimate gadget for this job. And as this quote from the source explains, it's designed to do something very clever. It ignores the boring part, where the particles are just flying through empty space, and zooms in only on the interesting part, the interaction itself. And what's really mind-bending is how it does this. You can think of the S operator as a kind of cosmic fast-forward button. No, seriously. It takes the state of the system from the infinite past, way before the particles could ever meet, and instantly transforms it into the state in the infinite future, long after they've scattered apart. It captures the entire story of the interaction in one single, elegant mathematical step. So let's just take a step back and look at the bizarre reality we've just built. It's a reality built not on physical things, but on questions. A world where the state of something is just everything we know about it, where the future is nothing more than a set of odds, where time itself is just a matter of perspective, and where a single operator can tell the entire story of a particle collision from the beginning of time to the end. This is the fundamental logic of our universe. And that leaves us with one final, absolutely massive question. If the solid, predictable world that we can all touch and see is truly governed by these strange probabilistic rules, then how does our normal everyday reality emerge from all this quantum chaos? Well, that remains one of the deepest and most fascinating mysteries in all of science. Thanks for diving in with me.